Okay, so the kinetic theory of gases. Here's where we get to think about the gases as individual molecules, and we get to think about what these molecules are doing and how this relates ultimately to the parameters of temperature and potentially pressure and volume that we've talked about. All right, so this is the way that the idea starts. We're going to start with an ideal case. So this is an ideal gas once again, but you have a collection of molecules of the same gas present in a unit of volume. Let's say this cube presented right here with the x, y, and z axis. All right, so if you start with the 6 molecules of the gas, the premise is that they are going to be moving with some amount of velocity. But they are free to move in every which one direction. And if you just statistically try to determine where they could go, well, you only have 3 different axes in this cube. There's only 3 dimensions. And so the 6 gases are, statistically speaking, going to subdivide themselves into either going to the x-axis, to the y-axis, or the z-axis in terms of the movement. And that means that if you're moving on the y-axis, you could be moving left or you could be moving right. So here we have the 2 portions of the same gas moving left or right with some velocity y or speed y. The ones that are going up and down are moving in the z trajectory, and the ones that are moving in and out are the ones moving in the x direction. And they all have the same average speed when it comes down to this. Now the idea right here is that there is equal probability of these gases moving, up and down or left and right or in and out. There's nothing restricting them from going every which way. And given enough time, they're going to go in every single direction that they have possible within the 3 dimensions. Okay? But the idea is that on average, the velocities are going to be the same on the x, the y, or the z. All right, now if you start thinking about what pressure is, and we defined this in the last lecture. Pressure is the force that the gas exerts on the walls of this container divided by the area of the face of the container to which the pressure is being exerted. And technically speaking, what we're talking about is how much energy or how much force are we imparting from the gas molecule onto one of these faces of the cube. All right, now this is where I'm going to get a little bit more physical, quite literally, on you guys, because I'll talk a little bit about the idea of force, which is totally a physics premise, but we're going to apply it right here, and we're going to see eventually how this comes back around to give us some information about the gas itself. All right, so force, you might remember that force is mass times acceleration, but another way to look at it is that force is the same thing as the change in momentum, which is represented by the Greek letter rho right here, divided by t. Or excuse me, the change in momentum by the change in time. So how much momentum is changing as a result of time? That's the amount of force that you have. And the momentum itself is the mass of the particle multiplied by its own velocity. All right, so we're going to substitute this term for rho over here. So we have force equals mv divided by t. All right, so now the premise is that the time that the gas takes to go from one side of the cube to the other side is simply the distance of that specific container, call it L, divided by the velocity by which the gas is traveling, right? So time can literally be expressed in terms of the length of the cube divided by the velocity. And when you do that, you're going to end up deriving that the force is the same thing as mass times volume, mass times speed squared divided by the length of the cube. All right, now let's take this form of the force of the gas and reintroduce it into the pressure expression. Specifically, let's divide mv squared over L by the area. Yes, so we're dividing this by LA. You could also interpret that as being Louisiana, but I guess LA, works too. All right, so the idea right here is that because we're dealing with a cube, well, the area of a cube is nothing more than L times L or L squared. So L times L squared becomes nothing more than L cubed. And L cubed is ultimately the volume of the cube. So the pressure itself is now determined by the mass of the gas molecule times its velocity squared divided by the volume of the actual cube or receptacle in which the gas is contained. All right, now this is the interesting aspect of it. As I told you before, the gas is free to go on the x direction, the y direction, or the z direction, and it has equal probability of moving in any of those three directions. And so at any one instance, there is 1/3 probability that the gas will move in the x direction, 1/3 probability that it will move in the y direction, and 1/3 probability that it will move into the z direction. And notice now that we're substituting the values of x, y, and z for the individual velocities as well, because now we're kind of referencing this in all three dimensions of the cube. But we can use this premise, the fact that the pressure of the gas moving any which way, doesn't really matter if it's moving in the x, y, or z direction, the pressure of the gas is going to be given by 1/3 mv squared times the divided by the volume. So let's start with that premise. All right, now if we actually multiply both sides, so let me go back to the previous slide. If we multiply both sides by the volume, we're going to end up with pressure times volume equals 1/3 m velocity squared. And in this part of the slide, I'm dropping the x, the y's, and the z's because it applies the same to all of them, right? So this applies to any one direction. It doesn't really matter where the gas is going. It's the same thing. Okay, so we have pressure times volume equals 1/3 m times velocity squared. All right, also, if we compare this to the kinetic energy is 1/2 mv squared. This comes directly from physics. So the relationship right here is that PV is in fact 2/3 of what the kinetic energy is, right? So 1/2 mv squared is the kinetic energy. 2/3 of kinetic energy have to equal PV. And the relationship right now is that because PV is dealing with the gas, and we can use the ideal gas law here, PV is the same thing as nRT. So nRT equals 2/3 of the kinetic energy. And ultimately, the kinetic energy itself of a gas is 3/2 nRT. And if you basically divide everything by n, you end up getting the kinetic energy per mole. Okay, so per mole, 3/2 RT is roughly how much kinetic energy the gases are going to have. And the beauty of this thing is that the kinetic energy is directly attributed to nothing more than the temperature at which the gas is being held. This is actually a very key component of stuff because now we have a measure of temperature and energy that goes back and forth with each other as long as you're dealing with gases. And I'm going to make this premise and make use of it in future lectures. But right now what I want you to understand is that the amount of heat associated with the gas is related to the temperature at which the gas is being held. Now going back to PV equaling 1/3 of m speed square, is that if you multiply both sides by 3, you get 3 PV equals mv squared. And now the idea is that PV is nRT. So I'm going to make that replacement. PV equals nRT. So make that substitution over there. And now dividing by the number of moles, we have mass divided by moles on the right side of the equation. Mass divided by moles is the same thing as saying molecular weight or molecular mass of gas. All right. So ultimately what this means is that the speed square of the gas is going to equal 3 RT divided by the molecular weight of the gas itself. And ultimately this means that the velocity or the speed of the gas, the average speed of the gas, is going to be the square root of 3 RT over the molar weight. So the derivation wasn't too crazy, but as you can see, it has to do entirely with the notions of physics, notions of force, momentum, and kinetic energy. But we're going to be using this particular format of the equation in future equations. I do want you to keep in mind the idea that the kinetic energy of the gas is completely based on the temperature of the gas, specifically 3/2 of RT. Okay, in the next video, we will investigate what this expression for the velocity ultimately represents. So I'll stop right here.